at Cambridge University with a Marrow Overends team. Rebecca is a PhD candidate in the Glass and Façade Technology Research Group at University of Cambridge under the supervision of Marrow. She was seconded to TU Delft in Holland in the autumn of 21, and is currently completing a 3-month research contract in partnership with TU Delft and Perma-Stelisa. Rebecca also conducts independent research consultancy in sustainability, which has included developing a bespoke model for the lifetime GHG emissions of an international shipping company, and more recently working to increase the rates of flat glass recycling in the UK, which is how I think I first met her. At Cambridge University, she has worked for an academic supervisor in environmental sustainability and business, and she delivered sessions to third-year undergraduate engineers for 3 years. Rebecca previously graduated with a Master's in Materials Science and Engineering from Manchester, which included a 1-year industry placement at Siemens Magnet Technology, where she worked as a student process engineer. After graduating, Rebecca worked as a research assistant under supervision of Professor Philip Withers. So as you can see, she is hugely knowledgeable, hugely talented, a very nice lady. I've met her on a number of occasions, and her current PhD research examines the roles of material efficiency in facade design. And Rebecca's talk is entitled "UnFixing Facades, the Pursuit of Material Efficiency from Design to Second Life." So, Rebecca, I hope I've done your introduction properly, and I'll hand over to you, Rebecca, to deliver your talk. Thank you very much.
Thank you very much, Chris, and thanks for the invitation to share my research today. I do just have to admit it's not doctor just yet in terms of completing my PhD, but hopefully soon. So I'll just share my presentation if I can.
That was purely your expectation, Rebecca.
It's fine, yeah, wishful thinking, it's good.
Wishful thinking.
Okay. I think you're going to see the wrong one for now. Can you see the right screen now? Is that okay?
Looks good.
Okay, great. Thank you.
You can see that, yeah.
Okay, well, thanks very much for the introduction. My name's Rebecca, and I'm currently finalising my PhD thesis in exploring material efficiency within facade design, and looking at how the decisions that we make at the design stage affect what we can do with materials and components at the end of life in terms of recovery and reuse. So I'll give a brief introduction into the scope of this talk today. In terms of the motivation for looking at sustainability in the built environment, there's 3 main challenges really we face as a society, which I imagine everyone on the talk is well aware of, but just to set the scene, we have the first challenge in terms of rising greenhouse gas emissions, which we are using to power society as it is today. Secondly, we have increasing use of raw materials, which may be affected by resource availability in years to come. It's not necessarily a case of that we're running out of raw materials, it's just a case that it's potentially becoming more and more difficult to source the materials we need to actually power society today. So if we're thinking about moving to renewable technologies and energy transition, we need a high amount of critical raw materials, which may become more and more challenging to actually source in the first instance. And then thirdly, a challenge in terms of actually rising levels of construction and demolition waste, which in the US is expected to double in the next 3 to 4 years, which is really quite a considerable amount. And it's something that we need to be mindful of in terms of when we're designing for construction to make sure that we're not adding to this problem in years to come. And so these challenges also relate back to energy. And if we look at global energy consumption, it can be split into 4 different sectors, which is proposed by the International Energy Agency. And these fall into transport, buildings, industry, and other sectors. And where construction sits is from the buildings in terms of in operation. This contributes around 30% to total global energy consumption. And then we have the additional amounts that come from actually producing the raw materials and manufacturing the products that we use in buildings today. So that adds an additional 10% to the total mix attributed to buildings. And that energy consumption then also translates back to global carbon emissions or greenhouse gas emissions. So I just want to break this down. If we were to look at absolute demand for energy and the corresponding CO2 emissions, and we imagine that to be the area of this circle on the slide here, there are different approaches that we've looked at to try and address reducing CO2 emissions as a whole. And the one that's been a big focus of policy to date is looking at supply side efficiency improvements. So this is really looking at fuel switching, so looking to use low carbon fuel sources, moving away from coal and gas, and also simultaneously decarbonising the electricity supply. So the focus of this is really trying to reduce the carbon dioxide equivalent for each unit of energy that we consume. But what's received less focus is a demand side efficiency improvements, which is actually looking to reduce the absolute energy consumed globally. And we've seen some attention being put onto this in the last 30 to 40 years in terms of construction and more closely the facade design, in terms of improving energy efficiency and incorporating behavioural changes of buildings in use to reduce energy consumption of buildings. But from the material point of view, and where my research is focused, is looking at improving material efficiency and how we actually construct the parts and components for buildings today. So just give a short brief introduction into the concept of material efficiency. It's often also termed the circular economy, or as a strategy to move towards the circular economy. And in that instance, there's an idea of a recovery hierarchy, which has been put together by several different organisations and has seen many iterations over the last 20 years. But the general concept is trying to break down parts and components to try and minimise wastage throughout product life cycles. And in the first instance, trying to reduce consumption and think about whether it's actually necessary to produce components in the first instance. So I think if we step through this hierarchy, in the first instance, we're looking at actually reducing and refusing new designs as much as possible. So I suppose one clear example that sort of rings to me on this theme is the building in London, the Tulip, that was rejected over embodied carbon and heritage concerns, which is fairly recent, but for me that just sort of highlights this idea that actually this idea of material sustainability is becoming more important, or at least actually cropping up onto the radar a lot more in terms of, are we getting the value back for the buildings that we design in terms of what we have to put in to get that value in the first place. And then the next approach to the sort of inner circle of this diagram, the darker green, is looking at actually when we have designed a product and it's spent a period of time in use, how can we ensure that that product life cycle can be extended as far as possible? So looking to reuse and remanufacture products so that we're really trying to reduce energy inputs in terms of designing for new buildings. There's one example that's been developed in the structural steel industry, where there is actually certification now for performing testing methods and reconditioning strategies for structural steel framework components, which has helped to try and push the actual application of structural steel reuse in practice. And I think we're not quite there with facades yet. And then the next part of that hierarchy is recycling. And I just want to emphasize the point of recycling here is post-consumer recycling. So it's recycling of parts after it's had a period of time in use, not the internal recycling, which doesn't actually deliver an energy benefit from a life cycle point of view. And there has been some positive steps in this in the UK. And one example you may have heard of before is Morley Glass and Glazing in the north of the UK, which has developed a machine to be able to take out glass from insulated glazing unit frames and take that glass back to the glass manufacturer, Saint-Gobain, to be able to recycle and reprocess it back into new flat glass. And so if we take the life cycle of the facade today, we can map those material efficiency strategies from the last slide onto these different steps in the facade life cycle. So the first stage that we have is the embodied stage, which is it requires energy in terms of producing raw materials and getting it into a final product. Then we have the period of time in use and operation. And from a material efficiency point of view, we want to try and extend product use for as long as possible, so that we're actually limiting the amount of products that are coming out during the lifetime of a facade. And then we have energy associated with end-of-life management and actually reprocessing products and getting them back to the manufacturing facility, or ideally directly back to a building. And from the end-of-life point of view, it's really trying to eliminate any kind of disposal or waste in landfill as much as possible. And alongside that, eliminating manufacturing waste, so minimizing offcuts that might happen as a function of design. And just a brief sort of crude evaluation from the economic point of view on this. If we were to look at a new glass facade system, which might cost around £500 per square metre, the existing process of demolition for curtain walling units in the UK would mean that we typically would recover the aluminium and metallic framework components, and they'll be sold on at around £200 per tonne. But glass is often downcycled with other inert waste and sold on at about £1 per tonne. So there's a huge loss in economic value, and I think there's a significant work to be done in terms of looking at what the costs might be for new infrastructure and enable to try and narrow this margin as much as possible in terms of the lost economic value from these recovery processes. So this is where the research problem for my PhD sort of sits, is looking at this idea of the design of facades and how they've changed over the last 40 to 50 years, whereby in the past we might have been looking to make it as simple a design as possible, which might have very few different types of materials and components, and corresponding connection types between components and material layers. This enabled us to have potentially less embodied carbon from the initial outset, and also less changes in embodied carbon throughout the building lifetime. If we look at the graph on the right here, the embodied carbon is highlighted in green. But more negatively, this also influenced the fact that we have poorly performing buildings in operation and therefore have much higher operational energy over the building lifetime. But on the other side of that, as we move to these more operationally efficient facade types, we're potentially incorporating more material layers that might be of different compositions and more complex components, potentially more composite components that have a much varied lifespan. And so we want to understand, really, does this then impact the how does this impact the embodied carbon of the facade, not just at the initial outsets, but also throughout the lifetime in terms of component replacements, and actually try and understand how that matches then with what you might be able to recover at those component replacement changeover points and eventually at the end of life. So we want to try and make sure that purple shaded area on the bottom of the graph on the right stays purple and doesn't end up in grey, where we have a high loss of energy, where facades end up as construction waste. I think it's quite topical. A book called Biomimicry in Architecture, which I found a really interesting read, that actually described the modern day insulated glazing units as a monstrous hybrid. And monstrous hybrid was actually defined by Adam McDonough and Michael Braunert in Cradle to Cradle as a product that contains a mixture of materials or assemblies of components from which it is not economically feasible to recycle or salvage the raw materials after the current life. So are we continuing to develop these types of monstrous hybrids? And if so, perhaps what can we do better to be able to make sure that they don't stay that way when it comes to actually taking them apart? So So hopefully that's a short introduction really into material efficiency as a whole. I'm going to discuss some of the outputs from my research that looked at developing interviews and surveys across the facade value chain to understand the existing perspectives on facade reuse and how it might be possible to actually put in practice. I'll then present some work that I've been working on with Graham Colt, Exley O'Callaghan, which looked at actually mapping the UK glass value chain in terms of tonnage of products going into the different glass subsectors and looking at energy balance of different recovery strategies and how that might help support this idea of reducing energy consumption of the flat glass sector. I'll then discuss my research in developing a novel assessment method for measuring environmental performance in terms of circularity in the context of facades. And finally, just do a brief touch on some of the work that I've been working on in terms of the technological approaches to achieving high value reuse of flat glass and separating glass components more easily. So as I mentioned, in the first couple of years of my PhD, we worked to put together and define a survey and a series of interviews for the facade value chain to really try and understand what are the motivations at the moment for reuse. I do think these have even varied in the last few years, even since starting the survey and actually conducting the interviews. In some instances, this information was new and sort of the idea of even embodied carbon was a new topic, and in others, it was something that people were a lot more open to and thinking that could see it as developing further in the future. So this, the survey itself, we had around 69 respondents, right through from clients and developers through to architects and demolition contractors. And this gave us a really good idea of sort of how influential different stakeholder groups are in terms of actually influencing the design brief and perhaps making some decisions early on that can significantly affect the ability to reuse facade components. So in terms of outputs from the surveys and interviews, we worked to code all of the free text options and speech options and assign them to relevant themes. So this graph here is after coding the different free text options into these themes, which gives an absolute term frequency for the key words that were suggested in the interviews and the survey. So this helps to highlight what some of the key barriers are at the moment or perceived to be from across the facade supply chain. And what we found was technical constraints from the original design surrounding things such as functional performance, which also goes through to issues to do with risk aversion in terms of being able to actually specify a facade that is going to provide the same functional performance as new if it's been reused. So there's considerable concerns around warranty and being able to actually reissue that effectively. Other concerns around actually being able to disassemble components. Many respondents thought dismantling at the moment is over complex and simply not worthwhile. And quite a key barrier that we wanted to highlight and pick on is that people feel that at the moment there's a big lack of available information on the topic and awareness on why it would be good to design for disassembly. And those barriers actually, in terms of how they varied across the supply chain, it's quite key that it's quite interesting to see that it is split in terms of what seems very important to certain stakeholders and not so important to others. So on that topic of education and awareness, we saw that, so this graph shows the relative importance of these barriers to each stakeholder group. So what we found was that education and awareness topic for clients and developers and architects seems to be much more prominent, which we see is really quite key given that their position in the supply early stage of the design brief and supply chain. If they aren't aware of what they might be able to do to maybe focus on looking at factors to do with embodied energy, embodied carbon, material efficiency, why would they then even think about including it in briefs? So I think there's a responsibility there for the supply chain to help to sort of educate each other and push each other in the right direction to be able to actually address some of these challenges. And then from the main contractor and facade contractor point of view, there are more challenges around logistics and concerns over availability of supply of the reused materials. And then material processors are more concerned around functional performance, and demolition contractors more concerned about economic cost, which is really also quite significant and interesting that the demolition contractors feel that way, because they are highly motivated by essentially how they earn their income is by the fee that the client will pay for the build, and where the client specifies what they should do with the materials that are taken off. They have to follow that very closely and in the constraints of time that they're given on site to do that. So clients could potentially provide better support there. But they also earn income from actually selling on the materials that they take off the building. So if there is a demand for materials, such as there is for aluminium and steel metal components, where they can sell on at this high price, around £200 per tonne, then they will recover it. So we really need to sort of link these two sides of the supply chain up to make sure that where there may be new demand coming from clients and architects, demolition contractors are aware and actually supported to be able to deliver and meet that demand. The motivations for reuse, we found that it was quite a key opportunity to try and increase the and actually educate on the environmental value of reuse options, and of course also justify the economic feasibility that I've just mentioned. I'll just move through this slide now. We just then decided to map these key barriers and motivations really out onto a schematic diagram to try and highlight sort of where we see industry linking up potentially to try and deliver these design chassis in practice. And the findings of this also in the paper highlighted at the bottom of the slide, published just early last year. And so we see that this it starts with, or doesn't actually start, so it starts or end with this idea of actually motivating clients to actually start specifying reused products and increasing client demand. And we hope that will then therefore help to demolition contractors to be stimulated to improve take-back infrastructure and logistics. There's some key challenges to consider and think about in terms of what we do with existing facades. Do we deconstruct them on-site or off-site? Perhaps in some instances it's not so feasible for reuse to be an option, and then we move to higher value recycling and making sure the infrastructure is in place for that. And then supporting that from the manufacturer, going back to the manufacturer and material processor point of view, actually helping to deliver on higher recycled content and developing the right methods and standards for performance testing for facades as systems or subsystems and components. And then in the centre of this, we also see that it's important to increase information and engagement on this topic so that we can support and justify any kind of changes in these designs as best possible. And so that's trying to quantify environmental value in terms of reuse and increasing and communicating the available information of the existing stock of recycled materials, where perhaps there may be trade-offs, if there are any, in terms of aesthetic or functional performance, making sure material processors are actually able to communicate that with clients so that they can make a fair judgment themselves. And so I'll just move on now to another focus of my research has been to look at flat glass as a material and the efficiency of the UK glass sector. And this is the work that I've been working on with Graham Coulter, ex-Callahan, and we set out to try and map the UK glass sector as a whole. And so this graph on this slide shows a representation of all of the raw materials in glass production going into the different glass subsectors. So we have flat glass, glass wool, like container glass, and other glass products such as pharmaceutical industries. And so what this graph is trying to highlight, really, if we move through it from production through to primary application of glass products to collection and sorting, reprocessing, end of life, we can see that in terms of the recovery of the glass products after a period of time in use, it varies quite considerably between the different glass subsectors. So if we look at container glass production, due to an extended producer responsibility scheme and also a good collection infrastructure that's in place through your curbside collection, when you put your glass bottle in your bin out the front of the house or take it to a bottle bank, there are high levels of recycling in the container glass industry at around 60 to 70%. So that's helping to support high recycled contents in new container glass production. Whereas in the flat glass industry, we see much less collection. Although there is some internal recycling, which can be up to 25%, in terms of collection after a period of time in use, we're looking at values of potentially much less than 10%. So it will move through to your domestic or commercial construction. Flat glass will move through to those sectors and end up typically into aggregate production, because there is some motivation to try and avoid disposing in landfill, because there's a demand from the aggregate industry, and also there is some cost for disposing of glass in landfill, albeit lower than the general landfill fee. So we want to also understand what are the energy consequences of that sort of inefficiency in terms of material flow. And so this slide, just want to break down, if we zoom out a bit and look at flat glass production as a whole, what are the stages that where we have energy inputs and in corresponding emissions. So we have the raw material sourcing, which has an energy input associated with it in terms of sourcing, extraction of materials and processing. Soda ash is the main raw material that's energy intensive to produce here, because quite often in Europe it's produced through a chemical process, which is quite energy intensive. But we also have energy input associated with sourcing cullet. And so there are corresponding emissions with both of these options. We then have energy inputs associated with actually melting the raw materials, the batch raw materials to produce molten glass, and corresponding, so we'll have combustion emissions due to actually combusting fuel to produce the energy to power the furnace. But we also have process emissions associated with the raw materials, burning off raw materials. So carbonate raw materials that we have in glass production naturally release carbon dioxide as a byproduct of production due to the decomposition of them in the furnace. And that is really where those two factors are where the gains are to be made in terms of using cullet, because we can reduce both combustion emissions, because you don't have to take the furnace to its higher temperature, but also process emissions, because that thermal decomposition of raw materials has already happened in the first round of producing that glass. So that's when we know that cullet can have savings in terms of emissions, but we know that also then after molten glass has been produced, there are further indirect emissions associated with powering whatever electricity supply you need for forming the glass, and potentially any additional processes such as coating, laminating or toughening. So we took some of these figures and looked at just that stage. I mentioned the raw materials versus cullet sourcing and also producing molten glass, and understood that the use of 100% cullet in new flat glass production could save up to 27% in energy and 41% of equivalent CO2 emissions, and that's in those stages of 1 to 3. So it's a significant opportunity to try to tap into, and up to date with sort of this idea of the circular economy and looking at increasing recycling rates. Typically, we look at closed loop recycling, which is trying to get a product directly back to the same product, which has its value and is important in a lot of ways. I think we understand that it's not just necessarily the focus on the product alone, it's the material. So in terms of glass itself, the material that we want to try and get back is cullet. And cullet has a demand in not just flat glass, but also container glass and glass wool industries. And we see fairly similar energy saving can be made because it's the same technology effectively of melting raw materials and cullets to produce a molten glass product, which then has different secondary processing methods to get it to glass wool, container or flat glass. So we wanted to understand then, if we take 1 kilogram of flat glass output in its primary application, what would the energy savings be from different recovery options to those that we have today? So set about looking at 3 different recovery scenarios. The first one being a comparative scenario of typical recovery today, where we have high amounts of flat glass collected going to the aggregate industry and some going to landfill. And then the 2 other scenarios, which are sort of more idealized collection processes, which allows the collected flat glass to go to the glass wool, container or flat glass industries, so about 30% to each industry. So I'll just highlight some of the outputs of that piece of work for the first 2 recovery scenarios as a comparison. So this slide here shows all of the energy inputs associated with producing that 1 kilogram of flat glass output in its primary application. That I touched on that last slide. So where we have around 84% in architectural glazing and 16% to automotive. And so if we look upstream of that, we have all of these different energy inputs also associated with producing that the glass in its primary application. So we have the original energy input to produce the uncoated flat glass, and then the additional processing steps. Oh. Okay. And those also add other process. Is the sound okay? Yeah.
Sound is fine, Rebecca.
Okay.
Sounds fine.
Fine. And then, thank you. And then, so with those additional energy inputs, in terms of processing steps, those typically will go straight out to losses because you don't have a raw material that you're essentially producing from adding those additional processing steps. So they will be immediate losses, but the energy that we can save is that can be recycled back to glass cullet. So if we move through after that 1 kilogram of flat glass has been in a primary application, if we look at this collection that we have today, as I mentioned, with a high percentage going to the aggregate industry, in terms of recovered energy of that total input that we have, so from all the processing steps, there's around 0.4% of recovered energy based on where this existing collection infrastructure for flat glass. So I think we can do much better than that. And so that's why I wanted to look at this alternative recovery scenario, potentially going to, if we could actually collect all of flat glass and take it to the container flat glass or glass wool sectors. And what we found was that by improving the collection infrastructure, we could reach, and this is assuming 90% of flat glass is collected to this higher value glass recycling, we could reach a recovered energy of around 14.2%, which is, we view as quite significant and something that potentially we should be working towards. Of course, there's a balance between what cullet is actually available in the UK, but there hasn't been a clear study to try to actually quantify this effectively. And the one study that is available is potentially underestimating it quite considerably because it sort of mainly looks at just flat exterior glass, when actually interior glass also could contribute up to maybe 30 to 40% higher of that figure. So I think there's a big opportunity to be made in terms of flat glass collection and recycling and trying to actually decarbonise the flat glass sector. And alongside that, we will need the supporting studies that look into the economic feasibility of different collection methods. There'll be savings potentially due to lower energy consumption from using cullets, and that will hopefully lead to a cost saving and potentially also indirect cost savings from reduced carbon emissions, where there might be less taxes. So the UK has the emissions trading scheme, and so potentially there may be less taxes arising from reduced CO2 emissions in glass production. But all of this sort of needs to be balanced and understood better to try and actually stimulate the flat glass take back infrastructure. Alongside that, also there may need to be supporting legislation. There's good voluntary legislation in the Netherlands, for example, that supports extended producer responsibility scheme that helps flat glass get back into the supply chain, into these higher value recovery routes. So leave that there for today and just move on to another branch of my research, which has actually been to touch on that potential barrier motivation from the earlier studies and to understanding the facade value chain as a whole and what might motivate better design for disassembly methods. in which we've looked to develop a novel environmental assessment for assessing the end-of-life performance of facades. So why this is relevant, we've found that the envelope can contribute up to 25% of the initial embodied energy. And this is significant because it's not only that initial embodied energy, but also throughout the life cycle of a building, where an envelope might typically have a lower service life to other building elements, such as the structural site work. We may see high levels of recurring embodied energy throughout the life cycle of the building. And this challenge might also actually scale quite considerably when we look at facades, which consists of a wide number of components, each which might have their own service life, which may or may not also be depend on other neighbouring components, depending on how they're connected. So we have these facade systems with a wide range of service lives, and we want to understand how this might affect what you can do with the facade at the end of life. So to sort of illustrate this, if we take the inputs associated with a facade system over its life cycle, what we might be looking at is where we have an initial embodied impact at the start, so at year 0. And then across the life cycle, we'll have these potential recurring embodied impacts as a result of, as a consequence, of component replacement over the facade life cycle. So what we want to understand is, okay, then, so when you do replace those components, or you do take the facade down at the end of life, what might you be able to recover in terms of that initial embodied input? And potentially that's what you're able to recover could help to mitigate impact in the next facade life cycle. So we want to find an approach to actually be able to quantify this environmental value over time. So my research set out to first develop a new assessment method, then apply it to 4 different facade typologies and evaluate the outputs. So the different recovery and reuse scenarios that I considered in this part of the research are the first scenario being system reuse, where a system is taken from a building and directly reused on another building. Component reuse, where the system is taken down and carefully disassembled, and the components that can then be reused in a new system or elsewhere. Recycling as a third recovery strategy, which is where materials are separated fairly crudely at a 90% yield and reprocessed into their secondary application. So, for example, we might have aluminium going into secondary aluminium, or certain polymers potentially being recovered, energy being recovered through incineration. And then a fourth recovery scenario, which is where the sort of worst case and we want to move away from is any materials being disposed of in landfill. So these are the 4 scenarios that we want to compare through this assessment. And the mitigated impact that I spoke about before in terms of what savings might be made from using this facade in a second life cycle come about from the current system, so what we disassemble at the end of life, but also from the components that are replaced up until a point in time that we evaluate the reuse potential at. So for the components that are replaced, how we assess those in the model is by looking at this component reuse scenario. So as components are replaced, they can be directly reused in another system. And then for the recycling scenario, we consider that the replaced components are recycled to secondary application. And then the landfill scenario, they're disposed of in landfill. So how the assessment works is first it takes background data where we've assembled a materials inventory for all typical facade materials, which includes materials and all of their relevant processing methods. And from this, we also state the service life of those materials and any associated reprocessing costs for the materials into a secondary application. And also transportation is considered there too. And then secondly, in terms of the system and component reuse scenarios, we want to consider some kind of performance deterioration, because it's not quite fair to state that a component that's replaced at the 5th year may have the same value as it would at 25 years. So for example, an insulated glazing unit could be assumed that when it's replaced at 10 years, it will have the same value as at 50 years. So for that, we wanted to assign some kind of probability distribution in terms of probability of survival over the lifetime of that product. So for components, the probability of survival that's input in the assessment today is a log normal distribution about the service life of that component. So in the light coral curve that's plotted on this graph shows the probability of survival over time. And in the light coral curve, you'll see it's plotted for an individual component with a 10-year service life. So given that it has a 10-year service life, we see that at 15 years, there's a 30% chance that the component will have failed. And at 25 years, there's 78% chance that the component will have failed. So that's the probability of survival that's input in the system for components and how they might have deteriorated in performance. And then for subsystems, the probability distribution has been calculated from a study that found that looked at insulated glazing unit performance over time and measured actually how many insulated glazing units had failed at a 15-year interval and 25-year interval. And looked at around 700 units. So quite a large data set. And they found that around 2.7% had failed. And when I say failure, I'm talking about fogging of the units after accelerated weathering and aging tests. And so they found 2.7% had failed at 15 years and 3.6% had failed at 25 years. So we've used those figures to assign a probability distribution for subsystems in the system reuse scenario, and also for component reuse where components can't be separated into their individual components and have to be assessed as a subsystem. Those two factors are the materials inventory and probability distributions are the sort of background data for the model. And then we assign a systems inventory, which looks at each facade typology, and also a components inventory, which lists all of the components in the facade and relates back to their relevant material, potential and service life in that sense. And also the actual mass of the material to be able to calculate the embodied impact of the whole system and relevant subsystems. So that's the first calculation that the model will do, actually look at the initial embodied carbon of the unit under consideration. So these are the 4 facade typologies I've considered in this research for now. They're 4 glazed facades, 2 single skin facades, 1 double glazed, 1 triple glazed, and 2 double skin facades, 1 silicon sealed and 1 dry gasket sealed unit. And so the first output of the model is looking at this initial embodied carbon. And what we can see here from left to right is the single skin facade through to the double skin facade. And I must highlight that these figures are all assuming 0% recycled content from the materials used, just to provide a fair assessment when we're looking at that mitigated impact at the end of life. And this is really key because in terms of percentage recycled content, it can hugely vary the outputs of the model and the results in terms of embodied carbon or energy input. And so we see here that the large hitters, perhaps unsurprisingly, are glass and aluminium, and they take also a high percentage mass of the system as a whole. And so that's largely why we have that effect. I'll move on from this for now, but I'm happy to discuss this also at a later date to compare how these systems perform. But to highlight here, just the double skin facade typically add around 30% of embodied carbon to the single skin double glaze units, around 16% on top of the triple glaze unit. So they do add a higher initial embodied carbon input by having this extra material. So the next step of the assessment is then to look at how components can be separated effectively to enable subsystem or component reuse. And so what we do is we analyse, we have to first put together analyse the construction drawings and understand the different connections between components. So this allows us to then generate a system network of components which shows how all of the components are connected to one another, which then also affects the corresponding service lifetimes. So if we were to just to highlight this, look at exploded view of a double skin facade. This is the dry gasket sealed closed cavity facade. We have a wide number of components. As you can imagine, also there are a large number of connections between those components, which also vary in type in terms of being removable or non-removable. And why that is important, the connections themselves, is that if we were to, for example, take system X on the slide here, where we have 3 components, each with their own service life. Before disassembly operation, this system would have a service life of 10 years. That's what we could assume. But after disassembly, the component A would have a service life of 10 years. But the subsystem components consisting of components B and C would also have a service life of 10 years because of that permanent connection between component B and C. So this then relates back to those probability of survival functions and the factor that we incorporate in terms of the system and component reuse scenarios. So how these parts are connected is hugely important in terms of the output of the reuse potential. So this is a system network illustrated for the double glaze unit, the single skin facade double glaze unit. And don't worry too much about looking into this, just want to highlight the number of connections we have in the system and the level of reversibility between the different component and connection types. So what we see is in light grey are all of the reversible connections between components. So when there's a disassembly operation, these can be removed completely. And in the darker grey, we have the non-reversible connections. So they will have to remain when it comes to disassembly. Those components have to stay connected to one another. And so the first output that we use is the life cycle embodied carbon over time. And this varies between the system types. So if we look at this graph here, we're looking at the cumulative embodied carbon impact over 80-year period. And what you'll see is the double skin silicon sealed closed cavity facade has the highest embodied carbon impact over the 80-year time period. And these steps up in the curve are due to the component replacements that I mentioned before. So we have blind system motors and the double skin facade replaced every 15 years. This doesn't contribute that significantly, but there is a small step up at the 15-year interval. We also have laminated glass and insulated glazing unit replacement and other components being replaced over the life cycle. I'll move on for now and look at the final output of the model. In effect, is the reclamation potential at a certain time point. And so for the system and component reuse scenarios, as I mentioned, this is a function of the probability of survival and the initial embodied impact. Whereas the recycling scenario, it's a function of what material, where the component goes in terms of a secondary material application. So when we're looking at these different recovery scenarios, these are the three connection diagrams that you would see that the assessment will then actually analyse. So for system reuse, we're looking at the full system as a whole and the probability of survival of the full system. Component reuse, we look at actually disassembling all of the reversible connections and then reusing the components and non-reversible subsystems. And in recycling, we have just a comparison of the material into its secondary application. So this is an output of in terms of reclamation potential for the dry gasket sealed double glazed units plotted on this graph. So on the y-axis we have the reclamation potential as a percentage, and the x-axis is the age of the facade in years. And so what you'll see is for all stages there's an early drop in the reclamation potential, and this is because of the fabrication and construction stages of facades, so the stages A3 to A5 of the life cycle. But quite tellingly, so the recycling curve follows a fairly linear shape, and this is because we don't have this probability of survival function considered. And so the components, when they're replaced, they just go directly to their secondary application. And the average recycling potential changes over time. So these steps up and down are because potentially where you have potentially an average recycling potential at year 0, this will vary when a component is replaced that has a different recycling potential to the average. So for example, at 25 years, it drops down considerably because a component has replaced that has a low recycling potential. And then for the system and component reuse scenarios, what's quite interesting is to look at how they change over time in terms of which one is more advantageous. Quite noticeably, in the first few years, component reuse becomes the most favourable option of all three. And this is because when you have a component to be reused, you don't have to depend on another component potentially failing. So it's got a higher probability of performing in a second life. So this is a plot for the dry gasket sealed units, and I'll move on now because I know it was a bit tight on time, but this plot on this slide here is for a silicon sealed closed cavity facade. You can see it's slightly different in terms of which recovery strategy is most favourable over time, with recycling becoming more favourable at around 50 to 70 years compared to system and component reuse, simply because there are many more components in this double skin facade, but also because we have that larger lifetime embodied impact over time. So future development, we think it would be advantageous definitely to incorporate measured probability of failure of facades and their components in practice, and potentially other performance indicators to actually assess this drop-off in performance and the factor that we multiply the mitigated impact to for the system and component reuse scenarios. I think there could definitely be additional criteria for connection types and the ease of disassembly beyond reversible and non-reversible, which relates to the adhesive and non-adhesive connections, and potentially apply this to alternative facade typologies and different cladding types too, to start to really just develop a better feel of how different facade types perform in terms of end of life, disassembly and reuse. So just adding it as a new design metric to all of the other factors we have today. And finally, I'll just touch on the support that on research where I've been supported by the Society of Facade Engineers on looking at the separation of laminated glass in practice. So helping to move towards higher value reuse of glass, flat glass, or as directly reusing the component as flat glass, or being able to recycle the glass product at high value. So we know that laminated glass is being increasingly specified in new glass designs, but we want to really understand if it's possible to better separate the glass and the PVB interlayer to make sure that we're not also adding to the problem of waste and lost energetic value. So this is the test that we set up in Cambridge that actually is a standardized test for separating laminated glass components, where we have a steel jig that has an aluminium backing that then applies a force onto the glass substrate. So we have a force applied to the top edge of one glass sheet and the bottom edge of another glass sheet, and the interlayer inside is free to deform and shear. And so we have, in this instance, we have deformation of the interlayer itself, but also there's a force applied to the interface between the interlayer and glass, which then leads to complex behaviour in terms of how the substrates actually then fail. So what the type of failure modes we might see are cohesive failure, where the PVB deforms to such an extent that eventually it shears within the interlayer itself. We could also have substrate failure, where because we're operating at high forces, the glass itself fails, which is what we want to try and move away from, because obviously in that instance we aren't able to recover either material. But the ideal case scenario is looking at interfacial separation between the glass and PVB interlayer. And so we wanted to look at optimizing conditions that actually promote this method of failure of interfacial separation between the glass and PVB. And one key factor to consider, which actually owe a lot of thanks to Fred Fear at TU Delft for this comment, is the factor that we have the different sides of glass, tin or air, that may be bonded to the PVB. And just to monitor that in terms of testing, because we're actually in what we found by actually separating out these samples before testing is that there's a considerable difference in adhesion depending on which side of the glass is bonded to the PVB. So thankfully we separated out these samples into their different configurations before testing, and that allowed another variable to consider for the experiments. And then the other side was to look at humidity aging the samples before testing. So this is a sample that had been aged for 45 days at high humidity. And this, as you can see quite visibly, there's been moisture infiltration into the PVB or along the interface. And also the other factor to consider is looking at different temperatures. So looking at low temperature to high temperatures and how this affects the adhesion between the interlayer and the glass. And what we found is very different types of failure with taking into account these three different variables. So firstly, the configuration in terms of the tin or the air side to the PVB. When it's tin to PVB or air to PVB, we see this mixed mode of delamination. So it's almost as if the glass doesn't know which, the PVB doesn't know which side of the glass it wants to delaminate from. So we have this sort of mixed delamination that occurs on both interfaces of the glass sheet. So that's what you can see on this slide here. I'm just holding one of the tested glass samples at an angle to try to highlight that. And then for some of the samples, the tin air samples, we saw that the effects of aging can considerably affect the failure force at separation. So where without aging you might have glass fracture preferentially occurring, after a period of aging we saw around a 3 times reduction in the force at failure, and this interfacial separation between the PVB and glass, which is the ideal case in terms of looking at reuse or high value recycling of that glass, and also recycling of the PVB. And just then temperature was the other key factor, and we see at low temperatures you have to take the samples to such a high force that the glass preferentially fractures before anything interesting happens at the interface. And then at high temperatures, so going beyond a very interesting temperature regime around 45 degrees, we start to see the PVB fails preferentially. So we have this cohesive failure within the interlayer itself. But then there's almost a sort of sweet spot where the force can be reduced to a good amount, a significant amount, at around 35 to 40 degrees. That helps to initiate this preferential interfacial separation between the glass and PVB. So this is the sort of interesting area potentially for future research. And I'd just like to say, yeah, very thankful to the Society of Facade Engineers for supporting this experimental work and allowing me to also spend some time at TU Delft to look at this further. And so I'd just like to end there. Sorry for overrunning slightly in terms of time. I just want to sort of summarise in a short manner of the different sort of approaches and conclusions from the research to date. I think from the behavioural side of the research, the interview and surveys, we've seen that there's sort of a key barrier and motivation to really work on in terms of increasing awareness of these design strategies in practice, which then hopefully also will encourage willingness of different stakeholder groups to start thinking about these indicators at the early design stages, and hopefully also realise the responsibility in terms of advancing sustainability approaches. And then we've moved on to develop actual measurement of this environmental value, because how can we start to actually change design without having a clear measurement of what effect changes in design will have? So that's what the environmental assessment is hopefully working towards. And then quite key, although we know it's not the main barrier, and I think that other factors such as economics and actual the supply chain willingness is actually the main issue here. We think that focusing on also technical methods to retain value of materials is important to be considered to make sure that we're actually retaining as high amounts of materials as possible, and we're not having yield losses when it comes to recovering materials at low quality. So those are sort of experimental approaches that we see as future directions for the work. So thank you very much for your time today. I'd just like to extend thanks also to EPSRC, my research funding body, Society of Facade Engineers, and Also Graham Colt at Exeter O'Callaghan for investing in the research on the UK glass mapping. And finally to Permis and particularly Janneke Verkerk for supporting in terms of construction drawings to be able to actually apply the environmental assessment to actual facade typologies